Welcome back to the deep dive. Today we are taking a look at something that is, well, it's pretty much at the heart of all modern technology, but it's almost completely invisible.
We're talking about the chips inside your devices, specifically the massive systems on chip or SUPs that are being designed right now in 2026.
The scale is just, it's mind boggling. We're talking about designs that have up to 30 billion transistors.
30 billion, yeah. A number that's hard to even conceptualize.
Right. Just for context, the population of the entire planet is around 8 billion people. So you've got this digital city with more components than there are humans on Earth. And the challenge is, well, where do you put everything?
Exactly. You can't just feed 30 billion components to a piece of software and say, figure it out.
Yeah.
It's computationally impossible. The scale forces you to rely on a really old engineering principle, divide and conquer.
Okay, so this is where we get to the core problem they're trying to solve. It's called, and this is a mouthful, balanced hypergraph partitioning.
It sounds really intimidating, but the goal is actually pretty intuitive. You're just trying to break this enormous circuit into smaller, more manageable pieces.
Divided into, say, 4 8 blocks.
Right, and you have to do that while satisfying two constraints that are, competing with each other. First, the blocks have to be roughly the same size. That's the balance constraint.
You can't just have one giant block and one tiny one. That doesn't help.
Not at all. And the second constraint, which is really the one that determines performance, is that you have to minimize the number of wires that cross between those blocks.
Because every wire that crosses a boundary costs power and adds delay.
That's the whole game. You have to reduce that cut size as much as humanly possible.
So before we dive into how they do that, we have to talk about the model. Why a hypergraph? Most people have heard of a graph, nodes and edges like a social network. What's different here?
A standard graph is too simple for this. It assumes a connection, an edge, only links 2 points, 2 nodes, A to B. Right. But in a real circuit, a single wire, we call it a net, doesn't just connect two things. It might connect 3, 5, 10, sometimes dozens of different components all at once.
I see. So if you have one wire telling 3 different parts of the memory to wake up, that wire touches 3 places. A normal graph can't draw that.
Precisely. A hypergraph is the mathematical tool that correctly models that reality where one connection, a hyperedge, can link a whole set of components. The components are the cells, the wires, or the hyperedges.
Got it. Okay, so we've got a 30 billion component city modeled as a hypergraph. We know we can't find the perfect solution directly because it's NP hard. So let's unpack this 3-phase strategy they use to even begin to tackle it. So since you can't solve it directly, you have to use clever shortcuts, heuristics, and the go-to architecture for this in the industry is the multi-level framework.
Yeah, it's really a 3-step process. People call it shrink, solve, and refine.
Let's start with shrink. Phase 1.
That's coarsening. You can't work on the original problem, it's just too big. So you have to simplify it first. And you do that by iteratively merging groups of components.
So you take a bunch of cells that are really tightly connected and just treat them as one big supercell.
That's the idea.
Yeah.
You do that over and over again, creating a sequence of smaller and smaller, more abstract hypergraphs.
It's sort of like zooming out on a map, right? You go from individual houses to city blocks, then to whole neighborhoods. You're losing detail, but keeping the overall structure.
That's a fantastic analogy. And you can't just merge things randomly, of course. You destroy the structure of the circuit. We use heuristics to guide it, something like heavy edge matching.
Which means
it's pretty intuitive. You look for pairs of components that are already connected by the heaviest, most important wires. You merge those first.
Because they were probably going to end up in the same block anyway.
Exactly. You're preserving the most critical topological relationships. And this brings us to our first big engineering principle. Multi-level is king. You never, ever try to solve the full-scale problem first.
You just keep shrinking it. By about half each time?
Roughly half, yeah. Until you get down to a really, really small size.
And what's that magic number?
We shrink it until the number of components, let's call it $9, is down to 40 or less. Which brings us to phase 2, initial partitioning.
This is where you actually make the first cut.
Right, on that tiny 40-node graph. And this step, even though it seems small, is the most important one by far.
Why is that?
Because the quality of your final 30 billion component partition depends almost entirely on the quality of this tiny initial split. If this seed is bad, nothing you do later can really fix it.
It's like pouring a crooked foundation for a skyscraper.
It is. The whole structure is compromised from the start. No amount of polishing the windows on the 80th floor is going to fix that.
So once you have that critical seed, you move to phase 3, uncoarsening and refinement. The polishing stage.
Yeah, you start expanding those merged components back out, level by level. And at each step, you use an algorithm to refine the boundary, to make the cut just a little bit better.
And this is where the famous Fiducian-Mathias's algorithm, or FM, comes in.
That's the workhorse. It does all the heavy lifting during the refinement.
Okay, so let's get into the weeds on FM. It's a classic, but it has a big weakness, right?
It does. It's brilliant, but flawed. So, FM is what we call an iterative improvement heuristic. It looks at all the components right on the border of the cut.
The partition boundary.
Right. And it moves them one by one to the other side, always trying to find the single best move it can make at that moment.
And the genius is how it decides what the best move is. It's all about this concept of gain.
It's all about the gain. The gain is just the net change in the cut size if you move a component. You calculate it as the number of nets you set free minus the number of new nets you pull into the cut.
Nets set free, meaning wires that were crossing the boundary, but after the move, they're now totally inside one block.
Exactly. We call it the from side. And the to side are the nets that were safe inside the other block. But now your move has dragged them across the boundary, making them cut. You're always looking for the biggest positive gain.
But wait, checking the gain for every single component on the boundary at every single step. That sounds incredibly slow. How does this possibly run in a linear time on a 30 billion component chip?
Oh, that is the beauty of a clever data structure called the bucket array.
Okay.
Instead of scanning a long list to find the component with the highest gain, FM sorts all the movable components into buckets, and each bucket is indexed by its gain value.
So if a component has a gain of, say, +5, it literally just sits in bucket number 5.
Precisely. So to find the best possible move, the algorithm doesn't have to search at all. It just looks at the highest numbered bucket that isn't empty. That lookup is in constant time. It's basically instantaneous.
Wow. Okay, that's our second big principle then. FM is linear. You use this bucket array trick for lightning fast improvement.
That's the key. But this brings us back to the flaw. FM is fast, but it's also greedy. It can only see one step ahead. And that means it gets trapped in what we call a local minimum.
Right. It finds a solution that's pretty good.
Maybe even the best solution in its immediate neighborhood.
No.
But it can't see that if it made one or two moves that temporarily made things worse.
A negative gain move.
Yeah. It might be able to climb out of its little valley and find a much, much better solution on the other side of a hill. But it's too short-sighted to do that. It gets stuck.
So this is the flawed foundation problem again. If your initial seed, that 40-node cut, puts you in a bad valley to begin with, FM will do a great job of finding the bottom of that valley, but it can never escape to find the globally best one.
Exactly. The polishing is only as good as the stone you start with, which means we absolutely have to guarantee that first seed is perfect.
So how do you guarantee a perfect seed? This brings us to the most, I think, surprising part of this whole strategy.
It is. Because for that smallest, coarsest graph, the one where n is less than or equal to 40, we ditch the heuristics. We don't guess. We use exhaustive enumeration.
Exhaustive enumeration. You mean brute force. You check every single possibility. I thought that was always the thing you're supposed to avoid.
It usually is. But here it's actually feasible. And it's feasible for two reasons. First, n is small, only 40. But more importantly, we have that balance constraint.
Ah, right. We're not looking at every possible combination of 40 nodes. We only care about the ones that are a balanced split.
Exactly. We need to split them into two sets of roughly 20. So we're only searching what's called the middle level of the Boolean lattice, the sweet spot.
And how many possibilities is that?
For n equals 40, it's about 2.7 million configurations, which sounds like a lot, but a modern processor can tear through that in milliseconds.
If you can evaluate each one fast enough.
And that is the secret weapon. We use middle levels gray codes to do it.
Okay, gray codes. I remember those from digital logic. Every time the number increments, only one bit changes. How does that apply here?
It's the exact same principle. A gray code sequence generates the next balanced partition in the list by changing only one thing. In our case, that means moving exactly one cell from block A to block B.
Oh, that's brilliant. So instead of having to recalculate the entire cut size from scratch for all 2.7 million options?
You don't have to. Because only one cell moved, you can update the cut size incrementally.
Wait a minute, you just used the gain logic from the FM algorithm?
You got it. The new cut is just the old cut minus the gain of the one vertex that moved. That calculation is 01. Constant time. It's instantaneous.
So you're using lightweight brute force. You check every single option, but each check is so fast it doesn't matter.
That's the whole trick.
This is so interesting because you'd think a smarter algorithm would be better. Something like branch and bound, maybe?
Well, branch and bound, or B&B, is definitely smart. It tries to be clever by pruning the search tree. It says, okay, this path I'm exploring is already worse than the best answer I've found so far, so I'll just ignore it.
Which sounds good.
It does. But to make that decision, B&B has to calculate a really expensive lower bound at every single step. And for hypergraphs, that calculation is computationally heavy. It slows the whole thing down.
So B&B spends all its time thinking about whether to check something, while the gray code approach just checks it, because checking is faster than thinking.
That is the perfect way to put it. And that's our third key principle. Gray codes are the secret weapon. For a small enough problem, just enumerate every valid solution with constant time updates. It's faster and it gives you a provably optimal answer. No guessing.
Okay, so let's put this all together into the 2026 blueprint for partitioning these monster chips. It's this beautiful mix of high-level abstraction and then this incredibly precise surgical step.
That's it. So, step one, iterative coarsening. Shrink the problem down using something like heavy edge matching until you hit that magic n equals 40 number.
Step 2, the gray code core. On that tiny graph, you unleash a multi-threaded search. You split up those 2.7 million possibilities across all your CPU cores and find the one true global minimum, the perfect seed.
And then step 3, hierarchical refinement. You take that perfect seed and you propagate it back up through the levels. As you uncoarsen, you apply that lightning-fast linear time FM algorithm to polish the boundaries at each stage.
So the quality of the final 30 billion transistor design is basically guaranteed by the mathematical certainty of that initial gray code search.
It is. The whole thing rests on finding that provably optimal starting point.
So where does this go next? Is this a solved problem?
It's never completely solved. The new frontier is actually in machine learning. Specifically, people are using graph neural networks, GNNs, to try and improve phase 1.
The coarsening.
Yeah. They're training models to make smarter decisions about which components to merge at the very beginning to create an even better coarse graph before you even get to the gray code part.
So the AI is helping with the initial setup, the initial get.
It's making the shrink phase more intelligent, but, and this is the important part, the final ground truth, the thing that guarantees the quality of the seed, still comes back to that classic, rock-solid combinatorial math of the middle levels enumeration.
The math is still the final arbiter. So what does this all mean for you, the listener? We've gone deep into some pretty technical stuff, but the lesson here is really about strategy.
We basically covered 4 core principles. 1, multi-level is king. Always simplify a massive problem before you try to solve it. 2, FM is linear. Use smart data structures to make your refinement steps incredibly fast.
3, gray codes are the secret weapon. When your problem is small enough, don't settle for a good guess. Find the provably best answer with lightweight brute force. And 4, balance is a strict constraint. Use your constraints to your advantage to shrink your search space. We spent this whole deep dive on how finding that perfect starting point, that optimal seed, is the absolute key to solving these huge optimization problems. So think about that for a moment, but apply it outside of just circuit design. How often in your own life, planning a big project at work, or even just setting up a new routine for yourself, do we just take a quick guess at the best way to start because finding the perfect way seems too hard?
We settle for a good enough local minimum.
Exactly. The lesson here from the engineers designing the brains of our entire digital world is pretty clear. Sometimes a short focused period of exhaustive search for the absolute best initial setup can save you an unbelievable amount of time, energy, and cost down the line compared to just starting fast with a foundation that's, just okay. Something to think about for your next project.